So that's sort of EM at the level of the equations, but I thought it would be helpful to actually implement it and kind of mess around a little bit. So do you want to see what happens?
I would love to see what happens, Michael.
So I generated some data here, which comes actually from two different Gaussian clusters, one that's centered over here-ish and one that's centered over here-ish, just not to be too specific about it. But you can sort of see that there's two clouds of points, right? One in the upper left and one in the lower right. Can you see it?
The one in the lower right looks like a clown.
I think it's a little bit more of a superhero, but that's not the point. The point is that it's just a bunch of random points. That's the point. It's a random point, but it is a point.
So your point is that the points are randomly pointed?
Yeah, I just want to point that out at random.
I see your point.
And so what I want to do now is run EM. And the first thing I need to do is pick the initial centers, right? So I need to pick the mu's that we think these were generated by. And so a common thing for people to do is just to take two of the points from the data set at random. So I took 2 points at random, and I'll mark them with an X. And now what I'm going to do is run an iteration of EM. And what that means is I'm going to first do expectation, which is going to assign every one of these points to one of these two clusters, and I'll color them as to which cluster they belong to. And then I will move the centers, re-estimate the means based on that soft assignment.
Makes sense.
All right, now so what you can see is something kind of interesting happened. Because these centers started off in the same cluster together, many of them were assigned to one cluster, which was the one that was a little bit more above. And then very few of them ended up getting assigned to the lower cluster because very few points were essentially closer to that one than the other one. I colored the lower ones red and the upper ones blue. And there's this sort of band of ones in the middle that had intermediate probabilities. They weren't really very deeply one cluster or the other.
They were near 0.5?
Yeah, exactly. And specifically between including 0.4 to including 0.6.
Ah, okay. That makes sense.
All right, and so those are the green ones. And then based on the cluster assignments, re-estimated the means. So this X now is, the mean of the red points and the green points because these are actually shared. And this X is kind of the rest. And you can see it doesn't really capture yet what the true clustering is because a huge number of the lower right cluster points are blue. They're kind of grouped in with the upper left cluster. But we can run another iteration of EM. And now things have shifted, right? So now it looks like this lower right cluster has claimed a good amount of the points in the lower right, and the blue ones are the blue ones. There's just a few little greens scattered between them at the boundary, and you'll always expect some of that to happen. Now the centers have moved, and now they're starting to take on their clusters, but we can just run this a couple more iterations until we see the X is not really moving anymore. All right, it seems to have settled out, and you can see it really did pull out the lower right cluster as a cluster, the upper left cluster as a cluster, and just a few points at the boundary where it said, well, I can sort of believe that that's part of the red cluster. Or I could sort of believe it's also part of the blue cluster. I really can't decide.
And you know what? That's probably right, too. I mean, they could go either way.
Yeah, exactly. I can sort of hallucinate this green point here as being part of the upper cluster, just kind of on the fringe. But, it works just as well as being part of the lower cluster.
Actually, Michael, I'm kind of curious. Can you use your magical computer powers to click on one of those green points and see what the probability is?
I could. Yeah, so for this one in particular, it's 55% in the first cluster and 45% in the other cluster. So it really is, it's hovering near that boundary.
That makes sense. What about that red point all the way to the right, the one sort of all by itself?
Excellent choice. So it is actually 0.9999996 in one cluster and 1 minus that in the other cluster. This one is pretty certain coming from the second cluster.
I see two things that came out of this. One is EM is much nicer in that it's not forced to make a decision about where those green points go, and that's good. So that's sort of soft clustering does that. And that's a good thing because they don't have that problem that we had before. But one of the consequences of that, and this is not a bad thing, but it's a thing, is that even points that pretty clearly belong to one cluster or another, given that we're staring at them, they do have a really high probability, 0.999999996, but they all have some non-zero probability of ending up belonging to the other cluster.
And you think that's a good thing or a bad thing?
I think it's a good thing. I think it makes sense because Gaussians have infinite extent, and even if a point is very, very far away from the center, it has some chance of having been generated by that Gaussian. And so this just tells us what that chance is. It is very, very unlikely, but it is still has non-zero probability mass.
In some sense, it's acknowledging truth, right? Which is that you can't be sure which of the two clusters this came from, even if I tell you where those clusters are.
Right.
Yeah, okay, I agree with that.
Okay, so this is cool. So EM is nice. So does EM work for anything other than Gaussians?
It does. It actually can be applied in lots of different settings. Let's flip over and talk a little bit about some properties of EM.
Okay.